So here's example 1a. We are going to integrate from 0 to infinity of e to the negative x dx. All right? Now, definite integral, so defining characteristic, right? We've been talking about this all chapter long, defining characteristics. This is a definite integral, and one of my bounds is an issue. It goes to infinity. Now we're going to introduce limits. You have to use limits. You have to use limits. You can't just keep infinity as one of your bounds. That's not mathematically correct. So you have to use limits here. So I'm going to take the limit as b approaches infinity just because, and you type in a b or you put in a b or whatever it is because b is that value, e to the negative x dx. Then you integrate, right? You keep your limit as b approaches infinity. So this is negative e to the negative x, right? Because there's e to the x is just e to the x, but with that negative, you got to chuck one of those in front. And that is from 0 to b. Then you plug that in. The limit as b approaches infinity, and we use the fundamental theorem of calculus, so negative e to the negative b minus a negative, so plus e to the 0. Well, we know e to the 0 here is 1, right? I'm going to rewrite this. So the limit here as b approaches infinity of negative 1 over e to the b. Right? Do you see why? So if we can write this, I think it's easier to look at because 98% of success in mathematics is what? I hope you're all saying organization because that is the key. So 98% of success in mathematics is organization. If I take this b off to infinity, what does this whole fraction go toward? 0, right? Right, because my denominator is growing big and huge. So this is 0 plus 1, which is 1. And 1 is a number, is an actual value, so I know this converges. All right? Okay, let's try another one. I think we've got room. Yeah, we got a whole half a page here. Let's switch our colors up. Here's example 1b. I'm going to integrate from negative infinity to infinity. Ooh. Top and bottom bound. And what do you notice right here? Yeah, good. So take care of those bounds. Now, here's the deal. Whenever I go to plug in some value, I know negative infinity and positive infinity. As long as you pick something that works in the denominator. Well, this is our best day ever, folks, because we don't have any issues with this denominator, so you don't have to worry about it. But that is something to think about. You can't always just put 0 in there. If 0 is going to cause a problem, you can't use it, right? But, or if there's some kind of asymptote issue or something along those lines, you just have to be aware of what's going on. So we're going to split this up. I'm going to take the limit as a approaches negative infinity of a, and I'm choosing my c value here to be a 0 because it's easy. So don't forget your dx plus, and then I'm going to take the limit as b approaches positive infinity, and I'm going to go from 0 to b of the exact same thing. Now, I could write this, if it helps you and makes you feel better, to do that. Does that look more like inverse tangent now? Yeah, right? So I'm okay with that, but just realize if the dx is on the top, that's the same thing as a 1. Okay. Now, here's the beauty of these problems. Once you figure out this first integral, it's the same thing as this one because you're still integrating the same deal. The bounds are the only thing that are the issue here. Okay, let's do it. So I'm taking the limit as a approaches negative infinity here of inverse tangent of x from a to 0. Plus my limit as b approaches infinity, whoop, 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 not negative, infinity of inverse tangent of x, and I'm going from 0 to b there. So plug it in. If I'm looking at this, the limit as a approaches negative infinity here of the inverse tangent of 0 minus the inverse tangent of a plus the limit as b approaches infinity of the inverse tangent of b minus the inverse tangent of 0. Now, what is the inverse tangent of 0? 0, right? The inverse tangent of 0 is 0, 0 over 1, sine over cosine. So I know both of these are going to 0. Well, that's handy. Now, let's talk a little bit. So way back when we did inverse tangent in chapter 7, and I said, oh, tangent is one of the graphs, the inverse tangent graph is one you're actually going to use again. Welcome, ladies and gentlemen. Welcome to that time. It's cool, right? So remember your graph of inverse tangent. Right? What if I'm looking as a approaches negative infinity? So I'm going to negative infinity. What is inverse tangent approaching? Yeah, negative pi over 2. So this negative sign is that one, and I've got negative pi over 2. Plus, what is happening as my limit of b? As b approaches positive infinity, what's my graph going toward? Pi over 2, good. So, minus a negative here, pi over 2 plus pi over 2 is pi. And because pi is a number, this converges. Good. Cool, right? I think so too. Glad you guys agree with me. So in my head, I'm just thinking that you're agreeing with me. So let's just go with it. Okay, I'm going to do one more here. So I'm pulling one from the back of the book because I think this is a good example. So 8.9.19 is what we're looking at. I'm going from 1 to infinity of a 3x squared plus 1 over x cubed plus x dx. All right? You see the infinity, it is a bound, that's my characteristic, so let's do our limit right off the bat. Before you start integrating or doing anything else, it's automatic changing out that limit. So 3x squared plus 1 over x cubed plus x dx. Now, how are we going to integrate this? Yeah, do you see that? You see that u sub? I know that's what you guys are saying, I can feel it. Here, if my u is x cubed plus x, my du will be a 3x squared plus 1. Oh, look how fancy that is. Good stuff, right? Okay. Change your bounds. I am going to keep harping on that until it finally sinks in. Change your bounds. As soon as you do a u sub, you are changing your bounds. At x is equal to b, u is b cubed plus b. That's okay to have that. At x is equal to 1, u is equal to 2. Right? Because you're plugging those in. When you do a conversion, you're still taking b to infinity. But you have to change those bounds. And don't look back. Keep moving forward with your new bounds. I don't know how to say that any more than what I already do. So now this is 1 over u du. Natural log, right? Sweet. So the limit as b approaches infinity of the natural log of u from 2 to b cubed plus b. Plug that in. The limit as b approaches infinity of the natural log of b cubed plus b minus natural log of 2. Now what happens as b approaches infinity here? What happens to natural log? Y is equal to natural log of x. What happens to my natural log? It goes to infinity. So if my value goes to infinity here as natural log goes, it doesn't get there very quick, does it? But it does go to infinity, which means this is infinity minus the natural log of 2. So the whole thing goes to infinity. You guys are so good. So this whole thing goes to infinity. Natural log of 2 is a tiny little number. So that's not a big deal. But the whole thing goes to infinity, which means what? This one diverges. Do you see that? So if it's a number like we had previously, it converges. If it goes to infinity, like a problem like this, which is why I wanted to do this example, then that diverges. Okay. Good. Good job, guys, doing this.